All right, hi everyone. Thanks everyone for coming and joining our session today for running ML inference services in shared hosting environments. I'd like to introduce you quickly to our speaker, Danny Luo. Danny studied at the University of Toronto and is now a machine learning engineer at Nextdoor. He has a passion in actualizing the value of AI and proven experience in implementing ML solutions in large, complex enterprises. He's also an educator and also public speaker of ML. So I'll hand it off to you now, Danny. Thanks for coming in.
Thank you, Jotham. Very happy to be here with everybody. And I'm first going to share my slides, and then we'll get underway shortly. And Jotham, please let me know if there are any additional communication difficulties. So welcome, everybody. My name is Danny. I'm a machine learning engineer on the core ML infra team at Nextdoor. And today I'm excited to speak at the MLOps Machine Learning Production Bay Area Conference to share a couple of lessons that we learned running ML inference services in shared hosting environments. So let's begin. First, a little introduction into Nextdoor. What is Nextdoor? Nextdoor is a network where you can connect to the neighborhoods that matter to you. We are in 275,000 neighborhoods across 11 countries. In the US, nearly 1 in 3 households use Nextdoor, and we have about 29 million weekly active users. Nextdoor is based in San Francisco with several offices around the world, including Toronto, and a sizable remote presence. So let's talk a little bit about the Nextdoor ML platform. So we have over 30 ML models in production in multiple verticals: feed, notification, ads, etc. We serve over 85 million inference requests a day. And essentially, our ML platform is an AWS Elastic Container Service, ECS, collection of microservices, meaning that we have Docker containers on a shared host. They share CPU, memory, disk, etc. Per microservice, we have one model, and each service scales independently on CPU utilization. The model exists on the container, and it is preloaded into memory prior to serving when it spins up. And inside each container, we have multiple Python processes that are running our serving layer, which is either AIO, HTTP, or Flask. And we use a variety of machine learning libraries: TensorFlow, PyTorch, XGBoost, LightGBM, Scikit-learn, just to name a couple of the most predominant. Each container has the following qualities. Since we follow the classic 12-factor app design in these microservices, each container is stateless, meaning that it's in memory. It doesn't use a file system in the middle of a request. There's no database. There's no model or data database that it has to query or write to or read from for an inference. And as a result, there's no network I/O that's required for an inference. So once you receive a request from your client, you should be able to complete it entirely just with the without having to make a network call or make a DB call. So these things allow us to scale infinitely horizontally in theory. And so I want to center this talk around 3 main useful tips. In our 6 years of experience running the stack, we learned some, albeit painful, lessons about running ML inference services in shared hosting environments. So AWS ECS, GCP, or Kubernetes. And these 3 tips are: 1, start up healthy; 2, only do work when someone is watching; and 3, know what resources you own. So let's first talk about the first tip, starting up healthy. And this is going to be a 2-part story. The first is about warming models. So in these shared hosting environments, especially when we have cloud infra, hosts come and go a lot, especially if you have spot instances or GCP preemptible VMs. We have lots of container flux. So we need to make sure the new containers that we spin up are actually healthy before we start sending requests. And this could be as simple as loading a model into memory prior to receiving requests, but also, in addition, do doing a sample inference. And the reason why we need to do sample inferences is because certain model libraries like TensorFlow and XGBoost are notably lazy in how they initialize their variables at runtime. And this often causes a slow first inference when you have a TensorFlow or XGBoost model, which is especially bad when you're rolling a new fleet of containers at the same time, as this correlation of slow first inferences causes a pretty nasty latency spike. The second half of the story is related to the first one. Sometimes you'll have a slow container no matter what you do. And the moral of the story is if a container is slow, you don't want to keep banging on it. And again, this is especially important for deploys when you're rolling an entirely new array of containers. So this gets into load balancing. The traditional load balancing algorithm that we use in the application load balancer is round robin, which distributes tasks evenly, even if a certain container is slow. What we want to do instead is that we want to use least outstanding request, which sends new requests to containers or tasks with the least number of outstanding requests. And this offers a very valuable back pressure mechanism, meaning that we do not send new requests to containers with a lot of outstanding requests or unfinished work. In this case, even if there are slow containers, we don't overwhelm them and we give them a chance to recover. And you should do this anywhere where you have the opportunity to load balance. So you can do this at the application load balancer level, as well as if you're like us and you're running multiple Python processes inside a container to serve inference requests. You can do load balancing inside the container as well via Nginx or reverse proxies like HAProxy. And this segues pretty nicely into our next tip, which is only do work when someone is watching. So I mentioned before that it was maybe useful to do load balancing inside the container. And this tip is really about queue management. So what is essentially the story? The story is that you don't want to handle requests that your client has given up on. If no one cares about that inference, you should simply discard that inference. Kill the old requests using request queues. And for request queues, you can use reverse proxies, like I mentioned, like HAProxy, or Gunninghorn and uWhiskey. And this allows us to be able to recover from request spikes and prevent backlog of requests from piling up. Now, it's important here that you want to match the timeout of the queue with the timeout of the client. For example, the client gives up on the request after 1 second. You want to set the timeout of the queue to also be around 1 second so that when the client gives up on the request on the production, the queue can discard any unfinished inference and simply not even worry about it. And this is not particular to shared hosting. This is important in general, the idea of queue management. Especially important when you're running real-time ML inference services. And last but not least, know what resources you own. And so this is the most important tip that we have for running ML services in shared hosting environments. And to explain what we mean by knowing what resources you own, we're going to tell a longer story. And this story is about the curious case of the unscalable model. So one day, we're set up to release a huge model, which is an ML feed ranking model that we have at Nextdoor, a combination of XGBoost and TensorFlow neural networks. On the day of the release, we scale up ML feed ranking to 70% of full traffic. Even though we have an autoscaler that scales on CPU utilization, we manually scale up containers to match the sudden increase in traffic load so that we can give our autoscaler a break. By the end of the day, we see a couple of things. P95 latency looks okay. Right? It looks fine. It's not great, but it's manageable. The other thing is that we're running lots of containers at suspiciously low CPU usage, right? But things seem healthy, right? The latency is fine. We're not getting a lot of errors. Things seem healthy. But the next morning, things get bad. So let's take a look at what exactly happened. So prior to 8:30 a.m., we have these 4 graphs. You can see that as the day starts, traffic starts ramping up here on the bottom left request count chart. And as you can see, latency also slowly starts drifting up, and our containers also slowly scale up. So far, everything's happening as expected. And then around 8:20 a.m., we hit a sudden latency jump, and we absolutely fall off a performance cliff, as you see here in the top left diagram. And it continues to get worse with several jumps as new containers are being allocated. So latency is quickly maxing out. We see that slow containers are starting to come up, and we don't know why. After 45 minutes of investigation, we decide to throw more containers at the problem, throw more money at the problem. But some of the new containers are slow, and the old containers haven't gotten any faster. Latency is already saturated at 2 seconds, which is the timeout of our client. So our client gives up after 2 seconds for the request payload. We see that as we add more containers, we have a lower CPU utilization, as you see here on the top right diagram, which means a more distributed load. And given that request count is relatively stable, we should see that latency should be recovering. But no matter what we do, latency is refusing to come down. Finally, last-ditch effort, we throw more containers at the problem. CPU utilization continues to drop. Load is more distributed, but it doesn't help. And finally, around 10:20 a.m., we give up, we turn traffic off. Now, in the coming weeks, we do a deep dive investigation on just exactly what happened. So the main problem is that latency rises with traffic, even as the number of containers grows, and even though load is becoming more distributed. And during our investigation, we see that latency problems are confined to the containers on a few hosts. They're particularly bad on big machines. So like this AWS instance with 72 CPUs on which we have containers. But there is no obvious resource contention. Container, host memory, CPU, container, host memory, CPU, network, disk, they all have low utilization. So the normal bottlenecks that we expect with resource contention are not there. So what else could it be? And this is where we start thinking that may be a noisy neighbor problem. So as we scale from sparse containers on a host to many containers on a host, we go from little resource contention to actual resource contention. And we start to see a subtle resource contention that's not typically visible with your normal utilization metrics. One thing that we do see is that page faults are strangely high. And what this means is that our containers, CPUs, are asking for a page of memory, for example, for instructions, that isn't available, which suggests to us that we are trying to execute on CPUs where stuff in memory simply does not exist. And eventually, our investigation leads us to a well-known package called OpenMP, which is an intranode parallel computing framework. It partitions your work into tasks and schedules, and then runs these tasks on threads distributed among your CPUs. And the reason why OpenMP is relevant is because it's heavily used for CPU computation by model libraries such as TensorFlow or XGBoost. And OpenMP has parameters to control the number of threads that are spun up, as well as which processors new threads are allocated. And it is precisely these parameters that are the root source of our issue. So first parameter that we have to worry about is the parameter that controls how many threads to run. And this parameter is OMP num threads. And it sets how many OMP threads to run. In the Docker container, you see in the Docker container the number of processors that are on the host, not how many CPU units are actually allocated to the container. And so what happens is that OMP num threads defaults to the number of processors on the host. What does this mean? For example, if we have 2048 CPU units, around 2 CPUs, and the host has 72 CPUs, then OpenMP will spawn 72 threads, which is way too many threads for the CPU resources that the Docker container actually commands. And we see that due to this over-allocation of threads, we have very poor thread scheduling performance. And so once we know what the issue is, the solution is very simple. We simply set OMP num threads to match the CPU resources that the Docker container owns. And we see that after this, the latency on XGBoost and TensorFlow models improves dramatically. And the reason, again, is because they're using OpenMP for their parallel CPU computation under the hood. Other thing that OpenMP controls that is relevant for us is where should new threads go. So you see on the bottom here, the very bottom number at the very bottom represents the order in which the OpenMP threads come up. And this represents the recommended option, which is for OpenMP to spawn new threads in thread contexts as close as possible to the existing threads. So for example, if thread 0 is in this thread context, we see that the thread 1 is spun up in a thread context on the same core. And thread 2 is spun up on the thread context on a different core, but the same package. Package meaning physical processing unit, and so on and so forth. This parameter is called KMP affinity. And the recommended flags, as I just mentioned, binds new threads to free thread contexts as close as possible to the existing threads in order to minimize the communication overhead for passing instructions to the thread. And obviously, this is assuming that you own all of the CPU's physical processing units and thread contexts on the host, meaning that you own the entire machine, which is not the case. And in fact, this is absolutely terrible for a shared host environment. And the reason is because the container might not own the nearest thread context on the shared host, or it may not be available when the thread executes. So we shouldn't be trying to do any type of optimization. The solution for us is to simply set KMP affinity to none. We don't bind to any particular thread context, and we simply use what is available to the container. And once we do this, we see that latency on tree-based models improves. And you can see precisely the point at which it went into production. And this is more so for tree-based models and not neural networks. And this may be specific to the implementation of XGBoost or LightGBM versus TensorFlow or PyTorch. And so what is the end result of our OpenMP parameter tuning? Well, we saw that tree-based models, P95 latency dropped from 300 milliseconds to about 60 milliseconds. We saw that TensorFlow neural network models, P95 latency dropped from 400 milliseconds to 20 milliseconds. And as a result of this, we are able to run our containers hotter without sacrificing performance. We're able to increase our CPU utilization from 10% to 50% while maintaining performance. And we could have turned this up even higher to 75%, but we want to play safe with deployments as some of our models don't have warming quite yet, and running at 75% CPU utilization is a little too hot for comfort. We also see at this point that page faults went down, signifying to us that we are actually utilizing our CPU efficiently. And previously, our CPU utilization was low because we were spending way too much time thread scheduling or accessing memory than actually doing our CPU processing work. And the reason why CPU utilization is important is because since we auto-scale on CPU utilization, we are able to hold our container count equal while 3xing traffic and achieving our full rollout of ML. So in conclusion, our 3 tips that we have: number 1, start up healthy. And this means that making sure that models are fully warm before serving traffic, and using LOR, load balancing, wherever possible in the ALB or inside the container to avoid overwhelming slow containers or slow processes. The second tip is only do work when someone is watching, using queue management tools such as reverse proxies to drop requests that the client has clearly given up on, and to prevent a backlog of requests during some type of spike. And finally, knowing what resources you own. Most libraries use OpenMP for shared memory parallel execution of CPUs. OpenMP flags are tuned for single machines or instances that you own completely. And in a shared hosting environment, such as ECS, or when you have lots of containers on a host, these flags are simply suboptimal because you may not own the CPUs that OpenMP attempts to use or attempts to assign threads to. And so the result is that you should set OpenMP parameters to match the resources that are actually allocated to your Docker containers. This is the core ML team at Nextdoor responsible for the ML infra. It consists of Richard Huang, myself, Danny Luo, Matt Terry, and Hamid Lakhani. We would like to thank the broader Nextdoor ML team for the cooperation during hard times. We'd like to thank the systems team for their help and advice in debugging these difficult issues. We would like to thank the ML Ops conference organizers for organizing a wonderful event on a topic, ML Ops, that is starting to garner more interest as machine learning becomes more widespread in commercial use cases. Finally, I'd like to mention that Nextdoor is currently hiring for machine learning engineers, data scientists, and software engineers. And to learn more, please visit nextdoor.com/jobs. Thank you all for listening, and I hope that you learned something useful from this talk. And now I'll send it back to Jotham for any questions.
All right, thanks so much, Danny, for that talk. It was very, very insightful and helping to explain how to overcome some of the challenges of implementing ML models. If anyone would like to also share any questions they have in the chat, you can see
Jotham,
yes. On the right-hand bar, there is a chat feature. If you click session and then under the chat.
Yes, I see that session.
Looks like your chat was so clear and so concise. All right, so we have our first question from Ting Luo. This person asks, could you give more details about how to set OpenMP parameters?
Yes, the OpenMP parameters in this case were environment variables. So wherever you have your container context, simply set it in that container.
All right, we have another question. This person is asking, where do these models run? Cloud, assuming this is from OpenMP implementation, or on edge?
Yes, thanks for the question, Parshad. So the Nextdoor ML stack is an AWS ECS, so it runs on containers, collection of microservices. So we run these on a container service on AWS on a series of shared hosts. And the hosts are your classic AWS EC2 instances.
Another question from Rui Hua. Is there alternative tools besides OpenMP?
OpenMP is not a tool that we choose to use explicitly. It's a tool that is used by many of the machine learning libraries, such as XGBoost and TensorFlow, under the hood. Now, there are ways that you could probably configure it to perhaps use something else. In that case, you have to dive a little bit deeper into the TensorFlow or XGBoost Stack Overflow.
Parshad also had a follow-up question to the previous one. This person asked, have you also used Ray?
No, we have not used Ray.
Another question from Parshad. Also, why OpenMP versus GPU implementations?
That's a great question, Parshad. In our case, we do not have the option to use GPU as we don't have that set up just yet. So obviously, if you can get GPU inferences up in your service and have it be reliable, that I presume that would be a great boost over any type of CPU implementation. And so in this case, it's if you were to use CPU or OpenMP, you have to worry about the resource allocation for that. I'm not quite sure if you can spin up GPU containers. You might have to spin up an entire GPU instance. And even if you can spin up a GPU container, there's also the question of how GPU resources are shared between containers. And so this is a general tip in knowing what resources you own. In this case, it applies to OpenMP. If you were to use GPU, I presume that unless you own the entire instance, you would also have to worry about resource allocation in that case.
All right, that's great. Well, if there are no other questions, thank you so much, Danny Luo, for coming and spending time to talk to us. For everyone else who is still on the chat, please be sure to check out our sponsor booth. There are a lot of very cool giveaways and companies to talk to. So thanks so much, and
Thank you,
we'll
everybody.
see you at the next session.
All right. Bye-bye.